Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation of this section B topical MCQ on 10.5, which is on halogenoalkane. So in this kind of section B type of topical MCQs, so option A refers to 1, 2 and 3, relevant to what they're asking. 1 and 2, relevant to what they're asking, would be option B. C is 2 and 3, and D is just option 1. Alright. So by default logic, we always go and check for option 2 first, which is what you have been taught in school by your teacher. So if I check for number 2 for this reaction, so I have 2 bromopropane. I will go and draw that out. Free radical substitution. Try to substitute CH to become carbon halogen. You have carbon hydrogen. You have carbon hydrogen, you have carbon hydrogen, so of course they can undergo free radical substitution. And then when you have elimination, so of course we can also have hydrogen there, like that and like that. You can of course undergo elimination, and you can also undergo nucleophilic substitution because you are a halogenoalkane. So what happens is you can become OH, for example, and then you kick out NABR. If you react with the NOH, that is called hydrolysis. Alright? Or in other words, the type of reaction or the mechanism specifically is nucleophilic substitution. So all 3 are correct there. So in this next question, so it's asking which of the following would be suitable for use in a fire extinguisher. So we need a flame retardant, and if you know anything about halogenoalkane uses, is that we are looking for something brominated. Okay, so brominated alkane. Alright. So HCl is not something you will use in a fire extinguisher. This is corrosive gas. It might put out fire, but you know, if you are spreading corrosive gas, so whatever people are there will be breathing in corrosive gas, and that is something you don't want at all. Okay, 3 is a very sensibly is an incorrect choice. All right, but 2 being a straight chain alkane containing bromine, so that can be used as a flame retardant. So these are factual questions actually. So brominated compounds are used as flame retardant materials because they are flame retardant. They resist getting on fire, so we use them in fire extinguisher. In fact, we also use them to make the fabric coating for firemen. You know, you don't want their clothing to be easily burn as well. You want them to be flame retardant. But here, of course, is a use in fire extinguisher, not necessarily to make the clothing. All right. So this next question, so it's asking which statements are correct for an SN2 mechanism. So when we have an SN2 mechanism, you can watch my topical playlist on there's a topical playlist on A-level organic mechanisms. It covers every single organic mechanism you would need to master in your A-level chemistry. So you should check that out to make sure that you don't miss anything and you can master every single one of those case studies. Yeah, you just never know when it will come on. Alright. So we know SN2 is a single step reaction. The 2 there refers to bimolecular, because you have the nucleophile, you have the halogenoalkane, which is typically primary halogenoalkane, in the slow step, which is basically the only step. Okay, so if we look at that, they say the formation of the intermediate involve the collision of 2 molecules or ions. I remember seeing this question when I did the yearly paper actually, so I'm not going to be tricked by that second time. When I did that yearly paper, when I saw this term intermediate, straight away I said 2 was wrong, and in reality the term intermediate is really badly worded, especially when you talk about SN2 mechanism. because we talk about a single harm reaction profile diagram, where that is what we call a transition state, because you don't really have an intermediate, all right? So there's a reaction progress or extent of reaction. I don't know my reaction is exo or endo, but I'm just assuming it's exo, okay? I'm assuming, all right? So what happens in that mechanism is, if I show you a mechanism, CH3, CH2, Br like that, delta minus, delta plus, you get a hydroxide. So we show all in one step, but in reality, what we will show is we will have the R group, we will have some sort of hydrogen there. So it's like trigonal bipyramidal, but it doesn't actually exist because it's a very high energy species, which is basically the transition state there. What happened is your hydroxide is coming in and your bromine is going out. You will have a transition state. You will have a negative charge, because negative plus no charge will give you negative. If you use NH3, there will be no charge. You know how to count charges, yeah? So this bond will get shorter because you are forming the bond, and this bond will slowly get longer, all right? And then eventually you will just kick out to form the product, like that, all right? So that is basically your transition state. We don't call that intermediate. So I remember I said that I hated that question so much because I made that mistake because I didn't check for option 3, alright? So at the moment, if you think about it, you do need two molecules or ions to collide, because the two there refers to the bimolecular. One of it and another one of it, the nucleophile and the primary halogenoalkanes, give you two molecules in that single step, which is the slow step. It's called SN2 because the 2 is bimolecular, alright? So that bit is actually very correct. It is this green bit that I don't like, alright? But that's what I meant by, if you're not sure, check for the other two options, alright? So one bond is being broken at the same time as another bond is being formed. Yes, as this bond gets shorter, it's the bond that you're forming. This bond will slowly get longer until eventually it breaks, alright? So 1 is correct. And if you go for the last one, a carbon atom in the transition state, you see, so they go and talk about transition state as well, is bonded fully or partially to 5 atoms. In fact, it is partially actually, because we don't have a carbon bonded to 5 atoms. These are partial bonds, alright? So what happened then is, like I said, this bond will slowly form and get shorter, this bond will slowly get longer, and therefore eventually break until you get the hydrolyzed product. So that is actually correct. Go for the partial because they use all, alright? So 1 is correct, 3 is correct, 2 must be correct by logic, alright? But as I said, this is the only term that is really ambiguous. This is definitely correct based on the 2, based on the SN2. The 2 refers to 2 molecules or 2 ions colliding together, okay, in the slow step. Moving on to the next question. So we're looking for examples of nucleophilic substitution. So it could be SN1 or SN2. We don't care. We just want nucleophilic substitution. If I check option 2 first, what do I have here? CH3I becomes CH3OH. You just add water in the presence of acid. This is hydrolysis. This is your hydrolysis, because you are breaking the Ci and you form COH, alright? So that is your nucleophilic substitution, because hydrolysis is the name of the reaction, but the type of reaction is still nucleophilic substitution, right? That's the mechanism by which it proceeds. And I showed previously using this particular example in the question 8, if that was what you skip, alright? So this example was precisely what I showed here. Using bromoethane, the hydroxide attacked that, SN2 mechanism, primary halogenoalkane, 2 molecules involved in the slow step via the transition state. So this is SN2. This is definitely nucleophilic substitution. The next bit is also nucleophilic substitution, except that you have a 3-carbon halogenoalkane now, and it's still a primary halogenoalkane, so it's still going to prefer SN2, but here your transition state will not have any charge, because instead of hydroxide, you have a neutral nucleophile. neutral in the sense there's no charge on the nucleophile. So your transition state will still be like this, but you will have H3N, because your bond is between nitrogen and carbon, and your carbon-bromine will slowly break, and you will have no charge because well, ammonia has no charge, this has no charge, your transition state will have no charge. All right, so all three of them are examples of nucleophilic substitution reactions. So the next bit is an apparatus setup in the laboratory. So what preparations could this apparatus be used for? So you see there's a condensation. So you have a condenser to condense whatever you are heating to collect it. All right. So if you have ethanol from ethanol, so this is just a partial oxidation of ethanol. You heat it and then you distill it immediately. So this is a distillation apparatus, because whatever that you heat, lower boiling point, goes out as a gas, doesn't escape because you close the tap, and then it will go to the side, it get condensed. This is not a reflux, so it's perfectly fine. You will get the aldehyde. The next thing is ethanol. If I check number 1, ethanol with bromide and corn sulfuric acid. So if you remember your group 17 chemistry, corn sulfuric acid is a stronger oxidizing agent than Br2. So with Br minus, what you will get is you will get HBr and you get HSO4 minus, but then this is the acid-base reaction, and then you can get further redox, which I'm not interested in. I'm interested in this. This is how we generate HBr fresh, and this HBr is what is used to substitute the OH in ethanol to become like that, using the HBr fresh from the reaction of bromine and corn sulfuric acid. And you know this is an example of nucleophilic substitution, because in the previous question we talk about not that I forgot what it was but I definitely covered in one of the topical questions as well. Yeah, so bromoethane, sodium bromide ethanol. So ethanol would have hydrogen bonding between their molecules, so this will have higher boiling point than this, which only have permanent dipoles. So this can be distilled because this would have lower boiling point than ethanol. All right, so that is perfectly fine. To do with boiling point, you need to distill off something with lower boiling point than your reactant. 1,2-dibromoethane from bromine and ethene. Okay, I can tell you this is not suitable because ethene is a gas at room temperature and pressure. In case you don't know, that is a gas at room temperature and pressure. Yeah, you learn about properties, you learn about homologous series, physical properties back in GCSE, IGCSE or O-level. And because there's a gas, how are you going to react the gas with the bromine in the flask like this? Doesn't work. Yeah, the gas will just escape. All right, so that doesn't work with 3 because of the ethene. So only 1 and 2 are correct. That will be option B. And that's the last of the 5 questions in this 5 question series. If you enjoyed the tutorial, click the subscribe button on the bottom right and share the channel with friends, your class chat groups, your juniors, your seniors from school, anyone else really you think this channel will be useful for. Alright, see you in the next video and thank you for watching.